This is the 8th lecture of my series on vector calculus. In the last lecture, we had made a foray into vector algebra, and there we had picked up a few new entities like the Kronecker delta symbol and the epsilon symbol. So let me quickly recapitulate the basic points of the last lecture. One of the first things that we had talked about there was the Einstein summation convention, in which repeated indices are to be summed over. Here, I must stress that we had already adopted a notation in which x, y and z components would be replaced by the numbers 1, 2 and 3. And so, something like a vector being equal to ax I hat plus ayj hat plus azk hat would become a1 e1 hat plus a2 e2 hat plus a3 e3 hat, which this convention will help us write down in a compact fashion as ai ei hat. Similarly, ai bi ci will be a1 b1 c1 plus a2 b2 c2 plus a3 b3 c3 plus, in fact, the sum will go on up to an, bn, cn if we are in n dimensions. In what follows, I am going to assume that we are stuck to our three-dimensional world, so I will actually run over 1, 2, 3. All indices, unless otherwise mentioned, will run over the values 1, 2 and 3. Now, one major player that we met in the last lecture was the Kronecker delta symbol, and it was introduced through the dot product of the basis vectors ei and ej. ei dot ej turned out to be 1 whenever I is equal to j and 0 if I is not equal to j. This is simply the statement that the unit vectors that we are using are of unit length and are orthogonal to each other. This thing was abbreviated by the symbol delta ij. And one very important property of this Kronecker delta symbol is the following. If it appears in a sum, here for example when I write down delta ij aj, the j index is repeated, so according to our convention it's going to be summed over, then the sum can be carried out very easily. The delta symbol will go away, and whatever the summation index is, wherever it appears in the rest of the expression, it will be replaced by the other index. So here the summation index is j, the other index is I. So in the rest of the expression, that is in aj, the j will be replaced by I, and so we will end up with ai. Keeping this in mind allows us to carry out sums involving the delta symbol very, very simply. Our next major player, the Levi-Civita epsilon symbol, epsilon ijk, was introduced through the cross product. If you take the cross product of two basis vectors ei and ej, the result is going to be a vector, so it can be expanded in terms of the basis vectors, and that expansion was written down in the following form: epsilon ijk e hat k. Of course, k is being summed over here. And from what we know about the basis vectors and their cross products, things like I cross I is 0 or I cross j is k and so on, we can immediately write down the non-zero values for the epsilon symbol. Although the epsilon symbol can have 27 different values, I, j and k taking 3 possible values each, ultimately only 6 of them are non-zero, and these are epsilon 1, 2, 3, epsilon 2, 3, 1 and epsilon 3, 1, 2, in each of which the indices are a cyclic permutation of 1, 2 and 3. And value for this particular set is plus 1. And if the indices are an anticyclic permutation of 1, 2 and 3, namely 2, 1, 3, 1, 3, 2 and 3, 2, 1, the corresponding epsilon symbol is minus 1. This can be summarized rather succinctly by stating that epsilon ijk is the completely antisymmetric symbol in 3 indices that guarantees that whenever any two of the indices match, you get a 0. And all the non-zero values can be easily stated here just by giving this additional piece of information that epsilon 1, 2, 3 is plus 1. Now, using the epsilon symbol, we can easily write down the cross product of two vectors in terms of the components. A cross B simply becomes epsilon ijk E hat I aj bk, and A dot B cross C, the scalar triple product, takes the form epsilon ijk ai bj ck. And we had explained in the last lecture that epsilon ijk ai bj ck, if you were to expand that out, you will end up with a determinant in which a1, a2, a3, the components of the vector A, form the first row, the components of the vector B form the second row, and the components of the vector C form the third row. Although we did not really state this explicitly in the last lecture, but this is pretty easy to understand from what I've just said, that A cross B itself can also be written down in the form of a determinant. Here, E1, E2, E3, the three basis vectors will form the first row, components of the vector A the second, and components of the vector B the third row. The one very important result that we had derived in the last lecture was this identity involving a contraction of two epsilon symbols. A contraction means that you're multiplying the terms together and then you're also adding up. Here, the dummy index I shows that you're actually adding up over all possible values of I. And when you do that, the result is actually non-zero only if jk and lm belong to the same set, and the final result can be easily stated in the form of this identity. Epsilon ijk times epsilon ilm is equal to delta jl delta km minus delta jm delta kl. This particular combination of delta symbols is easy enough to understand and also pretty easy to remember. All you have to remember is, once you write down the indices of the two epsilon symbols next to each other, barring the dummy index, which is being summed over, the other free indices go in this fashion. If you take the first free index of the first epsilon with the first free index of the second epsilon, and of course that forces you to take the second free index of each together, then you get a plus 1. So delta JL delta KM with a plus 1. If on the other hand you cross this over, that is barring the dummy index, if you look at the two free indices or two pairs of free indices and go first index with the second and second index with the first, then you get a minus sign. And one very immediate consequence of this is a very familiar formula that the vector triple product A cross B cross C turns out to be B vector into A dot C minus C vector into A dot B, a formula which is often referred to as a back minus cab formula. Now with this background which comes from vector algebra, we are going to go into the realm of vector calculus. We are going to write down our by now familiar members of the Holy Trinity, the gradient, the divergence and the curl in this new notation, and then make use of the techniques and the identities that we had learned about to simplify various relationships and identities involving the gradient, the divergence and the curl. So first, let us talk about the main entity in this whole picture, the del operator. After all three of our basic operations, the gradient, divergence and curl, can be written down in terms of this one operator, at least as far as Cartesian coordinates are concerned. And remember, we are working in Cartesian coordinates throughout here. The del operator is, well, it requires no further introduction, as I say. Just to remind you, this I del del x plus j del del y plus k del del z In the standard notation, but in the notation we are adopting, this is ei del del xi summed over I, that is e1 del del x1 plus e2 del del x2 plus e3 del del x3. And we are going to often make use of another abbreviation. Instead of del del xi, we are going to simply write del I. Like instead of del del x1, we are going to write del 1. So this is e1 del 1 plus e2 del 2 plus e3 del 3. And using the summation convention, the operator simply becomes ei del I. So wherever we use a del operator before, we can use ei del I. So the gradient of phi, grad phi, is simply ei del I acting on phi, and that is ei del I phi. Of course, this tells you that the coefficient of the ith basis vector, the ith component of this, is del del xi of phi, which is something you already knew. So, at least this new notation is not changing anything that we already know. Let's go to divergence next. Divergence of A is del dot A, at least in Cartesian coordinates, and therefore it's ei del I dot aj ej. Now, in this case, we have to remember that the del I and aj, although they look like components of a vector, they are different in character. Aj in general would be a function of x, y, z, whereas del I is an operator. So del I and aj will not commute. However, ej can be taken to the front simply because ej's are constant vectors, del i's don't really act on them. Or if del I acts on ej, you get a 0. So ej can be simply pulled out along with a dot sign. So you get ei dot ej del I aj. Ei dot ej is of course delta ij, and as I have said, in any summation involving the delta symbol, you just replace the index being summed over by the other index. So if we decide to add up over j first, this becomes del I ai. So that's the divergence. Del I ai, of course, if we decided to add over I first, this would have turned out to be del j aj, but that would also exactly be the same. Finally, we come to the curl, the third member of the Holy Trinity. It's del cross A, so ei del I crossed with aj ej. Again the same thing, I cannot pull the aj across the del I, they don't commute, but ej can be pulled out and you end up with ei cross ej times del I aj. And ei cross ej, of course, is epsilon ijk ek del I aj. So, the curl can be written down as epsilon ijk del I aj, ek. So, the kth component of the curl of A, something we are going to need quite often in the future, is epsilon ijk del I aj. You should notice that I and j are dummy indices which are sitting in the first two positions of the epsilon symbol. Of course, you could also write that as epsilon kij del I aj. The k, the component you are looking at, would be sitting at the front, which is maybe easier to remember. The next two indices are ij and del I aj here. Notice that epsilon ijk and epsilon kij are exactly the same. So there is really no difference in the two expressions. It's just that very often it's easier to remember that the kth component of curl has an epsilon symbol beginning with a k. And the two other indices are dummy, ij, del I, aj. So now that we have introduced this new notation in the context of grad div and curl, let us try to see how useful this can be. We will make use of the notation and associated techniques to derive several important identities involving the gradient, divergence and curl. These identities will be primarily of two different types. In the first category come the identities where a single of one of these operations acts on a product of two entities. And the second kind will involve the action of two such operators in succession on a single entity. We will begin rather modestly, trying to prove a couple of identities of each kind as a warm-up before we go on to more complicated problems. First, identities involving a single operator acting on products of two entities. One, for example, that we can talk about is an identity involving the product phi and psi of two scalars on which the gradient is acting. The del operator or the gradient is simply ei del I, in this case acting on phi psi. So this is really ei, the basis vector, times del I acting on phi psi. And del I acting on a product, remember del I is nothing but the ith partial derivative, is simply del I phi times psi plus phi times del I psi, the way in which you differentiate products. So this breaks up into two pieces, ei del I phi times psi plus phi times ei del I psi. Now ei del I phi, that's nothing but grad phi, and ei del I psi is nothing but grad psi. So you get grad phi times psi plus phi times grad psi. One more product identity. Divergence of the product of a scalar and a vector. Divergence of phi times a vector. That in our notation is simply del I acting on phi a vector's ith component. Of course, this is to be summed over all I, as the notation implies. Now, the ith component of phi a is phi times ai. And when you do del I on that, remembering once again that this is a derivative, you are actually doing phi times del I ai plus del I phi times ai. Let me point out that in here there are several things that you would have seen if you had written the sigma, which is being hidden here. This is really the ith derivative being done and then you are doing a sum over the 3. Here, you are actually differentiating a term and then taking the phi out of the sum simply because it's the same in all terms, and that gives the divergence. So this derivative and taking the phi out of the sum, all of this is being done here under the radar. You don't have to keep on worrying about those processes because that's taken care of automatically by the notation. Of course, in addition to this, you have del I phi times ai, and that's grad phi dot a, right? Because this is the ith term. This really is grad phi's ith component times ai, and that's nothing but the dot product of two vectors. So you end up with phi times divergence of a plus grad phi dot a as divergence of phi of a. We will come back and prove many more identities of the first kind soon. But before I do that, let me introduce you to a couple of examples of identities of the second kind. Again, very simple ones to begin with. We are still in the warm-up session right now. Indeed, the identities that I am going to prove for you now are not really new ones. We have already proven them using components in previous lectures. These are the two identities which lead to a null result. The fact that the curl of a gradient of a scalar vanishes, so does the divergence of the curl of a vector field, provided the fields are smooth. Let us try to see how our new method helps us to prove these identities. So let's first prove curl grad phi is 0 using our new notation. Since you have met the curl in this new notation very recently, let me still remind you that curl of a vector field A in this new notation is simply epsilon ijk ei del j ak. Curl of grad phi is going to be epsilon ijk ei del j, grad phi's kth component. But grad phi's kth component is of course del k phi. So this is what you get. Epsilon ijk ei del j del k phi. This of course is a mixed partial derivative, repeated derivative done on phi. Now what I am going to do is make use of the fact that all three of the indices here, I, j and k are dummy indices and can be renamed at will. In particular, you can name these two indices whatever you wanted, including just interchanging their names. So I could call this epsilon I kj, ei, I've not changed that, del k del j phi. But now notice that epsilon I kj is the negative of epsilon I jk, because there's a single flip of j and k. May takes you from here to here, so you get a minus sign. And del k del j is the same as del j del k. Mixed partial derivatives are the same in whatever order you do them, as long as a function is smooth. And we are assuming, of course, here that phi and in the next proof, a vector are smooth fields. So what we end up with is curl grad phi, which is equal to this, is also equal to negative of itself. And the only thing which can be negative of itself is 0. So that's why you get this. The proof of diff curl A being 0 follows almost similar lines. Divergence of a vector field A, remember, is given by del I AI. So here divergence of curl of A will be given by del I. Curl of A's ith component. And as I have said before, curl of A's ith component is given by epsilon symbol with I at the front, then two dummy indices. I have chosen J and K here. I could have written them to be anything else other than I, that is. Then del J AK. So this is the same as epsilon I JK del I del J AK. I can pull the epsilon I JK out of this del I simply because epsilon I JK is a constant. Partial differentiating with respect to xi gives you 0, so you can pull it out of the partial derivative. We will now play the same game of interchanging indices. In this case, interchanging the first two indices, I and j. Calling them j and I respectively will give us epsilon j I k. I have to do it consistently. So this I also changes. So j and this j to I, del j del I ak. But now we have the same situation once again. This is a single interchange going from here to here. So this is negative of epsilon I jk. And del j del I ak is the same as del I del j ak as long as ak is a smooth functions. So this quantity is actually negative of itself, so it has to be 0. Let me once again urge you to try writing down complete proofs of these two results along with the new notation proofs and compare for yourselves how much more efficient this new version is. These were simple results for which the efficiency is there but it's not that pronounced. For more complicated theorems that we are going to prove, the efficiency that you gain by using the new notation will become even more apparent. Okay, warm-up time is now officially over. Let us go back to what I've called identities of the first kind and try to derive a few more identities which are more involved than the ones we have seen so far. Let me remind you that identities of the first kind, according to the classification I am using, are identities where a single entity, single differential operator, either a gradient or a curl or a divergence, acts on a product of two entities. The example I am looking at right now is that of curl of a scalar field phi times the vector field A. And using the definition of the curl, I can write this as epsilon ijk del I, the vector field phi A's jth component, ek. Before I go any further, let me comment that this is slightly different, at least on the face of it, than the curl expression that I have used before. The expression that I have used so far essentially went like this. Curl of A is epsilon ijk e hat I del j ak. However, I am fully free to change my dummy variables. One of the things I can do, and I have done before, is permute them cyclically so that this becomes epsilon k I j ek del I aj. This expression is exactly this, except that I have moved the ek to the back. And of course, instead of aj, I have written phi a as jth component. And epsilon kij, the epsilon symbol that I have here, is exactly the same as epsilon ijk. Remember, cyclically permuting the indices does not change the epsilon symbol. Proceeding from there, the next step would be to figure out that phi a, the vector field's jth component, is actually phi times aj. And then apply the differential operator del I, del xi on this product. And that simply gives me del I phi times aj plus phi times del I aj. This is simply del I acting on a product of two things. So if I break open this bracket, I get epsilon ijk. Del I phi is nothing but that phi's ith component, aj, ek. And that essentially is an expression for the cross product of two vectors. Remember, A cross B was epsilon ijk ai bj ek. By the way, I don't remember, but I may have introduced A cross B in the form epsilon ijk ei aj bk. But I would urge you to convince yourselves by cyclically permuting the indices here that these two expressions are really one and the same. So this is nothing but the cross product between two vectors, the vector whose ith component is sitting here, namely grad phi, and the one whose jth component is sitting here, namely the vector A. So you get grad phi cross A. The second term is even perhaps simpler to identify. It's phi times epsilon ijk del I aj ek, which is exactly this expression that we have been using. Rather, this expression with epsilon kij replaced by epsilon ijk. So this is curl of A. So curl of the product of a scalar field and a vector field becomes gradient of phi cross A plus phi times curl of A. Frankly, this result is not that unexpected, and it's pretty easy to remember. After all, the curl of a vector field gives you a vector field. Now, you also know that this is a derivative operation, so you should be applying the derivative on each term in turn, as you do in all derivatives. So it's not a surprise that you have one term in which phi is sitting alone and the curl goes and acts on A. The cross sign, or the deliberate confusion that we use when we talk about curl as del cross, which by the way works explicitly only in Cartesian coordinates, actually gives us a very nice way of realizing what this will be. When del goes and acts on phi, you get grad phi, that's a vector. And because of this cross sign here, it's easy to expect that you will get a cross product between grad phi and A. After all, the result has to be a vector field. So, this is sort of easy to understand. The one important thing that you have to remember is that the order is important. Phi A and A phi are the same things. But grad phi cross A and A cross grad phi are of course not the same. Here, specifically, the cross product has to be grad phi cross A. Let's move on to another example which is slightly more complicated. This is the divergence of the cross product of two vectors, divergence of A cross B. The beginning, of course, is straightforward. The divergence of a vector field is del I ai. Here it's going to be del I A cross B ith component, and A cross B, the ith component, is epsilon ijk aj bk. So, del I of epsilon ijk aj bk. The epsilon ijk, being a constant, can move out of the partial derivative, and you are going to end up doing a derivative on the product aj bk. And that, of course, according to standard rule for differentiating products, gives you del I aj times bk plus aj times del I bk. So, epsilon ijk is sitting outside as an overall factor. So now let's look at the first term. It's epsilon ijk del I aj. That's nothing but the kth component of the curl of A times bk. So curl of A is kth component times bk. That's the first term. Now the second term, well, aj is something you can leave outside and take the epsilon ijk with the del I bk. But if you're going to take epsilon ijk with del I bk, you have to remember that now I and k are going to be the dummy indices. J, at least as far as this part is concerned, is free. It's of course not free overall. It's going to be contracted with the j in aj later. But at this stage, you can think of this as a free index. So this actually is the jth component of curl of B. But in order to get the jth component, you have to put the j index first. So to change the epsilon ijk into epsilon jik. Epsilon jik del I bk. That actually is the jth component of the curl. Now, in order that this switch can be done, you are actually interchanging I and j, at least to get here, and that's why you have a minus sign. So now, what you have is curl of A's kth component times bk, and that of course is curl of A dot b. And here you have minus aj times curl of B's jth component, and that's nothing but curl of B dotted with A. So divergence of the cross product of A and B happens to be curl of A dot B minus A dot curl of B. Once again, if you think of the del as a differential operator, which it is, then it should not be too difficult to guess what this form is going to be. After all, you want to have a cross somewhere because you have an A cross B, and that you're getting in the form of curl of A here and curl of B here, and that will give you a vector field, so you must do a dot product with the other vector field in order to land up with the final result, which has to be a scalar field. What is not so easy to guess, however, is a minus sign in the second term. It's almost as if when the del crosses the A and goes and hits the B, it puts in an extra minus sign. Of course, as long as you keep the properties of the epsilon symbol in mind, this result is not at all a very difficult thing to do. As for me, I usually look up the result in a book when I need to use it. On a pinch, if a book is not available, then I can derive this quickly. And the quickest way to derive this is perhaps the one that I've shown you right now, using the epsilon symbol and summation convention. Moving further up the level of complexity, we meet our next identity. Once again, it's A cross B that we are talking about, but now we are talking about its curl. The beginning is pretty straightforward. Curl of any vector field is epsilon ijk E high del j, that vector field's kth component. But now, A cross B's kth component has to be written down as epsilon kln albn. Note that now that I'm introducing new dummy indices, L and M in this case, I have to be very careful not to accidentally choose a dummy index that I have used again. So I, J and K are out. You have to use something else. Of course, here I've used the next two letters of the alphabet. So now we have epsilon ijk, epsilon lmk. Well, this actually was epsilon k ln, but I am going to make use of the identity that we talked about, the identity involving contraction of two Levi-Civita symbols. And there, the easy way to remember the contraction was to ensure that the index being summed over was in the same position in the two epsilon symbols. Here, it's at the back, so I changed the k here and moved it to the back. Since I did a cyclic permutation, klm became lmk, this caused no change in sign. The rest is straightforward. EI was already there, still here. Then you have to do del J on this product ALBM. So firstly, because of this contraction over K, this product of two epsilons give me this expression. Let me remind you once again that the way in which you can easily write down this expression is essentially take the two phi indices, the first and the second in the first term. That will give you a delta IL delta JM. And then you take the first index, that is I here, with the second index, that's M there, and second index here goes with the first one, which is of course L. So I end up with delta IL delta JM minus delta IM delta JL. And at the same time, del J acting on AL BM breaks up into two pieces. Del J AL BM and another term with AL with del J acting on BM. Now let us try to write down the overall expression by combining all these things together. You have two factors, two delta symbol involving factors here and two factors here. So of course the product ultimately gives you 4 terms. Now what I have to remember is the basic rule for summing up with delta symbols involved in the sum, which is whichever index you are summing up, that goes away and gets replaced everywhere by the other index. Now here I am actually summing up over all the indices. Note that the expression on the left has no phi indices. It's curl of A cross B. I'm not talking of the ith component or anything here. So there are no indices on the left hand side. So right hand side of course also has no phi indices. All the indices that you can see, I, J, K, L and M, all 5 are actually dummy indices. So I could decide to add up over anything first. But usually it's a standard convention and it's good to follow a convention in such complicated cases, that you would actually sum up the later alphabets first. That is, in this case, we will leave IJ to be summed up later. L and M are the things that you are going to handle first. So here, when your delta IL delta JM, the rule is these deltas will go away and everywhere the L will be replaced by I and M will be replaced by J. I and J of course will stay wherever they are. So if you look at this term multiplied by this, it's pretty easy to see what will happen. All the L's in this expression will become I's. That means this one will become I and the M's will become J. So this one will become J. So you have EI, del J AI, BJ. The next term that you have here is one you get from this and this. Here, of course, all the M's become I and all the L's become J because you're summing up over M and L first. So EI, of course, stays where it was. Del J also doesn't change. The AL becomes AJ and the BM becomes BI. That's what this expression will do for you. Well, the two other terms that you have are simply terms that you get by contracting these with this one. In the first one, the one with the plus sign, again, all L's become I's because of this delta and all M's become J's. So you get AI, EI of course is still there. This becomes AI. Then del J was always there, but BM becomes BJ. And this is what contracts with this to give you the last term. There the EI will stand, the AL will become AJ, del J will stay as it is, BM because of this will become BI. So this is the full expression. What is left now is to write this in a more familiar form in terms of curls and divergences and so on. Now it's easy to see that at least here you have an EI BI which is a vector B and you are multiplying that by del J AJ which is divergence of A. Similarly here you have EI AI which is the vector A and you have del J BJ which is divergence of B. Things are slightly more complicated with this term and this term. Here you have BJ and del J, but del J is not acting on BJ. So you have BJ del J and you can move the EI inside the del J. After all, EIs are constant vectors, to get EI, AI. This, of course, is a familiar thing. This is A vector. BJ, AJ is also something we had met in an earlier lecture. It's actually B vector dotted with the del operator. And this is not a field, it's actually an operator. So this is B dot del acting on the vector A. This last term essentially is very similar. You have AJ del J, and by moving the EI inside the del J, you get EI BI, which is of course B vector. So the four terms can now be easily identified in terms of the action of the del operator. The first term here is B dot del acting on A. This one is B vector into del dot A. This is A vector into divergence of B. And this one is A dot del again acting on B. I've just rewritten that once again, or rather reordered the terms a bit, essentially focusing on the del operator acting on the two terms. When it acts on A, you get A del dot B, that is of course A divergence of B. You also get minus B times divergence of A. So divergence terms are here in the first row. In the second row, you have the A dot del and B dot del terms, minus A dot del acting on B plus B dot del acting on A. Remembering which terms come with a plus sign and which comes with a minus sign here may be a bit difficult. Of course, you can always look up the result in a book, or again, if you don't have a book available, just use the basic properties of the epsilon symbol and work this out. The final example of an identity of the first kind that we are going to discuss in this lecture looks pretty straightforward on the face of it. It involves a gradient of a dot product of two vector fields, gradient of A dot B. Given the fact that we are actually trying to go from easier to more difficult identities, this may come as a bit of a surprise on the face of it. After all, gradient should be one of the simplest of the three operations. And the dot product is also typically much simpler than the cross. And the beginning of this calculation is pretty straightforward. The del operator is of course EI del I. And the only thing I have to remember is that when I write down A dot B, I cannot write it as AI BI because that would end up confusing the two dummy indices with each other. I will have to call it something else. So I've decided to call it AJBJ. And then the next step also is pretty straightforward. Del I acts on the product AJBJ, gives you del I AJ into BJ plus AJ into del I BJ. So far so good. The trouble is, writing this in terms of gradient, divergence, curl, etc. acting on some either A or B turns out to be surprisingly difficult. So what we will do is we will actually move away from this and start a bit from the back. In this case, I am being helped by hindsight. But if you don't realize why I am doing this, you will soon see. So instead of worrying about this right now, let's worry about this particular entity, A cross curl of B. Of course, that's pretty straightforward to work out. In our notation, it's going to be epsilon ijk, EI, AJ, and curl of B is kth component. That, of course, is what a cross product is. And we know that the curl of B is kth component can be written down as epsilon k LM del LBM. Once again, I have to be careful about my choice of the dummy indices here. I have already used up I, J and K. So the new dummy indices that you get have to be something else. I have chosen the next two letters as before. The next step is pretty straightforward. You have two epsilon symbols here. And because of this K index, there is obviously a contraction. So we can fall back on our familiar hopefully by now familiar formula for the contraction of two epsilon symbols. Of course, once again, what we need to do is move the k indices so that they sit in the same position in the two epsilons. So I rewrite this as epsilon ijk. This stays as it is, but this one becomes epsilon lmk. So now the dummy index is sitting at the last position on both the epsilon symbols. The rest is as it is, ai, ei, aj, del l, bm. The next step would be straightforward and familiar by now. I replace this contraction by its equivalent involving the delta symbols. Delta IL, delta JM, first, second with a plus sign. And first, second, first with a minus sign. Delta IM, delta JL with a minus sign. The rest is of course as it is. And once again, when I do this summation, I am going to sum up over all of the indices I, J, L and M. K is no longer in this expression because it has been summed up in this. And so now you no longer have the K. But when I do this sum, I will decide to do the L and M sum first, leaving the I and J sum for later. So when I look at this term, delta IL, delta JM, EI, AJ, del L, BM, I am going to sum up over L and M first, which means all the L's in this expression becomes I, all the M's become J. So you get EI, AJ, del I, BJ. And this term becomes minus EI, AJ once again. The del L becomes del J and you have BI. Now, this should begin to look like a rather nice thing because remember, in our expression for divergence of A dot B, we did have EI del I AJ BJ and EI AJ del I BJ. So EI AJ del I BJ, this term which we had there, we can now see. Of course, the problem is we have also got this term which wasn't there before, and we have another term which essentially is the same term with the A and B interchanged. But that should really give us a hint as to how to proceed. This term, the extra term is of course minus A dot grad, A dot del acting on delta B. But if you do B cross curl of A, that is interchange A and B here, you actually end up with the second term that we had in divergence of A dot B. BJ, EI del I AJ. Of course, all I do is interchange A and B in this expression and also A and B here, so get minus B dot grad A. So adding these two things together, A cross curl of B plus B cross curl of A turns out to be these two things added together, which is of course gradient of A dot B minus this and minus this. So the expression that we are looking for, gradient of A dot B, is simply what you get when you move these terms to the other side. So the final expression is rather daunting. It's A cross curl of B plus B cross curl of A plus A dot grad of B plus B dot grad acting on A. To summarize, here is a complete list of the identities of the first kind that we have proven in this lecture. Remember, our identities of the first kind are a situation where you have one operation, either gradient, divergence or curl, acting on a product of two entities. Now, given the kind of entities you have, different operations are possible. If what you have are two scalars, their product will give you a scalar, and the only one of the holy trinity that will act on that is a gradient. So that gave us our very first identity. Grad of phi psi is phi grad psi plus psi grad phi. If on the other hand you had a vector field and a scalar field, then multiplying them together would give you a vector field. You could calculate a divergence of that or a curl of that. That gave us the second and the third identity of the first kind that we had worked out. Divergence of phi times A is gradient of phi dotted with A plus phi times divergence of A. Whereas curl of phi times A is grad phi cross A plus phi curl of A. Now, if you come to a situation where you have two vector fields, you can take their cross product to form a vector field. And now you have the possibility of a divergence of A cross B and curl of A cross B. Divergence of A cross B is relatively simpler. It's curl of A dot B minus A dot curl of B. Curl of A cross B is a bit more involved. It's A times divergence of B minus B times divergence of A minus A dot del acting on B plus B dot del acting on A. The final possibility, if you have two vector fields, is that you can dot them together to form a scalar field. And now the only thing that will act on that is gradient. So gradient of A dot B gives us A cross curl of B plus B cross curl of A plus A dot del acting on B plus B dot del acting on A. In addition to these identities, we are also proven two identities of the second kind. These are identities where a succession of these differential operators act on a single entity. The ones we have proven so far in this lecture, a curl of gradient of phi is 0 and divergence of curl of A is 0. We have a few more identities of the second kind left to prove, and we will take them up in the next lecture. In the last part of today's lecture, let me just show you how you can use the identities that we have proven today in a physical context. For that, we are going to take a look at a rather familiar physics problem, calculation of the electric field due to a point dipole from its potential. Now, the electric potential due to a point dipole P vector at a point at a position vector r is given by the following expression. V of r is 1 over 4 pi epsilon 0 P dot r hat by r square. What might strike you is that in a dipole, the potential depends as inverse square of r and not as 1 over r, which is the standard dependence of the potential on distance for a point charge. Of course, you can think of a point dipole as two equal and opposite charges placed very close to each other, and from that you can easily derive this expression. The derivation essentially goes this way. If you have 2 point charges plus q and minus q at a distance from the origin of d by 2, in fact d by 2 vector is a position vector of plus q and minus d by 2 is a position vector of minus q, then at the point r, the potential can be easily found out from the standard expression for potential due to a point charge by just superposing the two potentials together. You get 1 by 4 pi epsilon 0 times q divided by length of r plus, that is distance of the positive q charge from that point, minus q by mod of r minus, which is the distance of the negative q charge from that point. Now, it's easy vector algebra to see that r plus, the vector, is r vector minus d by 2 and r minus is r vector plus d by 2. And using the fact that length of a plus b is square root of a square plus b square plus twice a dot b, we can easily write down the corresponding expression here. And all that is left is to now carry out a binomial expansion. If you are at a distance r which is very large compared to d, and that is what we mean when we are talking of a point dipole, you can easily expand this out using the binomial theorem after taking the r square out from these two brackets. Of course, it comes out as 1 by r, the familiar 1 by r in the potential. but you have two additional terms here now. And if you now expand this out to the first order in D, after all, D is small, so D by R is a pretty small quantity. If you just expand this out in the first order, you get 1 minus half of minus R dot D by R square from the first term. From that, you subtract 1 minus half into R dot D by R square coming from the second term. And if you collect these terms together, you simply get Q over 4 pi epsilon 0. These two together give you a single R dot D by R square. There's a 1 by R outside, so you get R dot D by R cube. And QD vector, the charge of one of these two charges times the displacement vector between the two charges is defined to be the dipole moment P. So you get P vector dot R by R cube, and R vector is of course R hat times the length R. So you get P dot R hat by R square. Mathematically, this is the origin of the 1 by R square term. Physically, what we can say is that the two charges which are very close to each other have potentials which nearly cancel each other out. So the 1 by R dependence gets cancelled out. What is left is the next order of smallness. For large R, of course, negative powers of R are pretty small. The 1 by R has cancelled out. What you are left with is the next order, which is 1 by R square. Now our job is to start from this expression for the potential and calculate the electric field from there. Now electrostatics teaches us that the electric field can be calculated from the potential by taking the gradient of V and affixing a minus sign. So it's minus grad V or minus grad of, in this case, 1 over 4 pi epsilon 0 P dot R by R cube. We are now in a position where we can make use of some of the identities that we had learned about earlier. 1 over 4 pi epsilon 0 here is a constant scalar quantity that can be pulled out of the gradient. At this stage, let me warn you that you cannot pull this out because it's a constant, but because it's a constant scalar. If you remember the rather complicated form that we had for the gradient of A dot B, you would realize that even if A were a constant vector, I could pull it out of the grad sign and write the result as A dot grad acting on B. You would also get an additional A cross curl of B kind of term. Now, in the rest, what we have is our first application of one of those identities. This 1 by R cube is a scalar, so is P dot R. So by using the identity that gradient of phi times psi is grad phi times psi plus phi times grad psi, we end up with this expression. Gradient of 1 by R cube into the other scalar P dot R plus 1 by R cube times gradient of P dot R minus 1 by 4 pi epsilon 0, of course, is sitting outside all along. Now we have to calculate these two terms individually. Now gradient of 1 by R cube, you could of course calculate this by writing R as square root of x square plus y square plus z square. And so this would become x square plus y square plus z square to the power minus 3 by 2, carrying out the derivatives and putting all of it together. But it would be simplest to evaluate this, rather obviously, in spherical polar coordinates. Because out of the three coordinates r, theta and phi that are there in spherical polar coordinates, only one of them, r, is involved in this expression. Now, if you remember, there is something we had worked out in our very first lecture of the series. Gradient of v in spherical polar coordinates is given by del v del r r hat plus 1 by r del v del theta theta hat plus 1 by r sin theta del v del phi phi hat. And this would go over in this special case where v depends only on r. Here I am using v for any scalar, not necessarily the potential. This would go over to del v del r r hat. So gradient of 1 by r cube is simply del r of 1 by r cube, r hat. Therefore, minus 3 r hat by r to the 4. Very straightforward. What about the other term, which involves the gradient of p dot r? Well, we can insist on using the identity we had derived a while ago. Remember, this was the identity. Gradient of a dot b is a cross curl of b plus b cross curl of a plus a dot grad acting on b plus b dot grad acting on a. And if you really wanted to do that, you would end up with gradient of p dot r is p cross curl of r plus r cross curl of p plus p dot grad acting on r plus r dot grad acting on p. Well, curl of r is 0. Now this is something which you may already know, but if you don't, let me just remind you that you can calculate curl of r very, very easily. This r vector, of course, has components x, y and z in Cartesian coordinates. And if you just wrote down the standard formula, the determinant form for the curl in Cartesian coordinates, you would easily see that each and every term in this involves derivatives of one of the standard variables x, y and z with respect to another. And therefore, all the partial derivatives involved are 0 and you would get curl of r is 0. In fact, this is a special case of a more general result, that curl of any function of r into r vector is 0. It would be easiest to prove this result using the expression for curl in spherical polar coordinates. Let's go back to our expression. Curl of r is 0, so this term goes away. Curl of p, of course, is 0. P is a constant vector. There's no point in differentiating that. Similarly, r dot grad is a differential operator acting on the constant p gives you 0. So these are the 3 0 terms that you get. P dot grad acting on r is the only term which is not 0. So p dot grad, of course, is px del x plus py del y plus pz del z, and it gets to act on this. Now when this operator gets to act on xi, the only contribution comes from px del x acting on xi, and that's just simply px into I hat. Similarly, this operator acting on yj hat will give you only one non-zero term, that coming from del y acting on y, and you will again end up with pyj hat, and similarly, the third term will be pzk hat. So obviously, the result is rather simple. It's just p vector. Now, this result is very simple, but this whole procedure of calculating this using the identity was not really very simple. It's actually much easier if you forget about the identity here and just try to evaluate p dot r from its very definition. Remember, p dot r is nothing but pxx plus pyy plus pzz, and you're taking the gradient of that. So what you end up with is del x of this whole expression times I. But out of this whole expression, the only thing which has an x in it is pxx. Similarly, the y component, the j hat coefficient, will be del y of this whole thing, but that's just del y of pyy. And finally, the last term is del z of pzz times z hat. And this immediately gives us p vector back. So the lesson here is that while those identities that we have derived are all correct and are very useful, you have to keep your eyes open. Sometimes it may be a much better idea to forget about the identities and try to fall back on the original definition of things. That may very well give you the easiest way of calculating something. Also, another lesson that was implicit in this whole thing was that sometimes you would have to switch to a different coordinate system in order to simplify the calculation. Anyway, from the formula that we had worked out a while ago, E vector was minus 1 over 4 pi epsilon 0 times gradient of 1 by r cubed times p dot r, which of course is minus 3 bar to the 4 r hat times p dot r, plus 1 by r cubed times the gradient of p vector dot r. which we have just worked out is P. Collecting all of these terms together, you get 1 by 4 pi epsilon 0 and overall 1 over r cube. Here you do have an r to the 4, but this r vector can be written down as r times r hat. So if you go to that, you end up with an overall 1 by r cube. So taking care of the minus sign here, you end up with 3 r hat dot p minus p vector by r cube. Now, the r hat dot p which is sitting in that expression should be very familiar. It is nothing but the projection of the vector p in the direction of r hat, something that you can call p vector parallel. So E vector works out to be 1 over 4 pi epsilon 0 3 times p vector parallel minus p vector by r cube, or using the fact that p vector is a sum of two terms, two projections in the direction parallel to r and perpendicular to r, p perpendicular plus p parallel. You can rewrite this as 1 over 4 pi epsilon 0 twice p parallel minus p perpendicular by r cube. Now to cast this in a more familiar form, at least a familiar form to people who have already studied some electrostatics, let's take a look at the geometry of the situation. Here you have your dipole moment vector p, and r hat is a vector which is a unit vector in the radial direction, and that makes an angle theta with p vector. We are using spherical polar coordinates now, with the angle theta being measured from the so-called z-axis. Here we are going to choose the direction of the dipole itself as our z-axis. So you have p parallel, which is a component of p parallel to r hat, plus p perpendicular, giving you p. Now it's easy to see that the length of p parallel is nothing but p times cosine theta. And it's of course in the direction of r hat. So you get p cos theta r hat for p parallel. P perpendicular of course is the magnitude of p sine theta, but note that theta hat is in the direction of increasing theta, in this direction, opposite to p perpendicular. So you get p sine theta minus theta hat for p perpendicular. So putting these two things back in this expression, we get E vector equals p over 4 pi epsilon 0 into twice cosine theta r hat, that's the twice p parallel terms contribution, plus sine theta theta hat coming from minus p perpendicular, divided of course overall by r cube. By the way, it may have struck you already that writing p dot r hat by r square in the form p cos theta by r square and using the expression for the gradient in spherical polar coordinates would lead to the same result, with perhaps a bit less labor. Just as the potential went like 1 by r square instead of 1 by r for a dipole, the electric field also falls off faster than the electric field for a point charge. Rather obviously, because the two fields due to plus q and minus q tend to cancel each other, and you get a 1 over r cube dependence for a dipole field. In the next lecture, we are going to go back to proving identities, in particular identities of the second kind, repeated applications of grad div curl on some single entity. And we will also talk about some physical applications of those identities and the ones I have derived today in the next lecture. Bye for now.